Welcome to the 74th video in our series about Unix tools. The topic is hard and symbolic links. We used symbolic links when we did the shared libraries, and I said I would have a future video that explains them. This is it. The topic is long and may take more than one video because of the ridiculous short time limit I get per video. A block device, and that's a hard disk, CD, DVD, NVMe, a USB thumb drive, those things are not really byte addressable. You can't read and write a single byte like you can an array in memory. The smallest unit a block device can read and write is called a block. For many years, blocks were always 512 bytes. But some modern hard disks now use 4096 byte blocks instead. And CD-ROMs were always weird. They used 2048 byte blocks. Many consumer, if I could spell, that would be great. Many consumer grade disks really use 4K blocks, but they have hardware that lies and says the device has 512 byte blocks. So your interface to the device uses 512 byte blocks, even though the hardware itself uses a translation layer. They do that to be compatible with old computers because most UEFI and most BIOS won't boot 4K reliably. And that's sad because UEFI was supposed to be the total rewrite of BIOS and fix that problem, but they didn't. I digress. Let me get back on topic. Think of your block device like this ugly ASCII art diagram. It has blocks starting at number 0, and it has, for n blocks, it ends on n-1 blocks. Every block is the same size, and so you can think of this like an array on the disk. But instead of having a byte in each element, you have a whole block, which will be 512 bytes, 2048 bytes, or maybe 4K bytes. The job of a file system is to store files on these block devices. In Unix, a file is considered an ordered stream of bytes. So the kernel simulates byte-level addressing within a file by determining what block the byte is in, reading the whole block into a buffer, into memory, updating the byte in the buffer, and then writing the whole buffer back to the block, because that's all you can do is write blocks, whole blocks. So you've got a 512 byte buffer for the 512 byte block device. Obviously, the details are more complex. Another typo. Since the kernel tries very hard to avoid reading and writing a block just for one byte. They try to wait until you've changed several bytes and then they write the block. Okay? It tries to keep an in-memory copy of blocks and updates those, and only when you issue a file close, a sync, which is short for synchronization, system call, or if the file system is unmounted, which on Windows, that's something like, the eject or the safely unmount. Only then will a good Unix kernel write the blocks back to the block device. Many people, as a safety measure, force a sync call every few minutes, and they use some cron job, or it can be built into the kernel, so that if the power is lost, only a few minutes of data is lost, because when it's in the RAM, in the memory, it's faster. But if you lose power, remember, RAM is volatile, so you'll lose all the data. And so the compromise is every few minutes, stop what you're doing, write all the data back to the block device, and that way you only will lose the last minute or so of data. How does the kernel know what blocks are in what file? because the hard disk itself doesn't have a concept of files. It only has blocks. Blocks have numbers. You can read or write. Give it the block number, and it will read or write that block to or from your buffer. So, normal file systems, which include ext4 and XFS, they use some kind of B-tree style data structure. Now, the details are ugly and we won't go into it, but you should know what a B-tree is. This allows the kernel to read any byte in the file if it knows the number of the block that holds the root node of that B-style tree. Could be B+, B star, and there's some other ones, but if you know the root node, you can walk the whole tree and find any block you want. Thus, each file in Unix is really accessed at the kernel level using the number, which is the number of the block holding the root node. And in this picture for Bob, it tells you the inode is 3, so that's the root node. And you can see here's one internal node that has pointers. This one points to another level in the B tree, but 17, 6, and 7, those actually are blocks on the DASD, and these zeros, because 0 is your boot sector, those are like null, and it says I've got room for more data, but I'm not using those. And then down here in 4, I'm using block 8, block 22, block 16, and I have room for 3 more blocks, but I'm not using them. If we think about Bob, and we think about the root here is at this block number 3, and blocks 3 and 4 are internal data to the file system or overhead. They don't actually contain any file data, so they're not shown down here, but they'd have to be on the disk somewhere. But here are the block numbers, and you read, 00, 01, 02, up to n-1, n-2, n-3 at the end. So when we look at this diagram, the first thing you see is a 4, but 4 points to another internal node. So 8 is the first block in the file. And if we come over here to 08, you'll see, yes, I don't know if I can mark just the one. Man, my mouse is not good enough. There we go. So there's the first block. And then 22 is our next block, block 1. And then we've got 16, which is block 2. And then these slots are not used, so we come back up a level and we go to 17, and there's block 3. And then we'd have 7, which is, boy, man, I don't know. Yeah, there's 7. And then the last one is here, block 5. We've got 6 blocks in the file, 0 to 5. And if you took that list, you can see there's the list in that order. And so this is the concept of how these files are stored in the blocks on the disk. Why do we care about this? Well, most humans are bad at remembering long strings of numbers. If you could remember all these numbers, you could access the disk without any file system. And that's what hackers who attack your system do. That's what recovery tools have to do, is they have to go find the blocks on the disk and figure it out. But most humans are bad at remembering that. We'd like to have some kind of name. And if you saw up here, I had a name, Bob. And that's what I want to call this file. And so we have a directory, and you've seen the directory when we do something like that. We've got these names over here. Well, it turns out if you do an ls-i, there we go, it shows these numbers. And these numbers are actually like that number 3 in the diagram. Those are the numbers of the root block, or the block containing the root of the data structure for the file. And so when you see Bob, you'll look up 3, and then you can go walk this tree, traverse this tree. Great. When you open a file using a path, the directory graph is traversed to find the record with a matching name, and then it looks up the inode number, and it can traverse the B-tree with that inode number as the root block. And of course, each file has its own root block and its own tree that it has to maintain. And then all the blocks that are not used by any file, they're free space, are tracked by a separate, I apologize for the typos, separate data structure. And some systems use a tree, some use a linked list. It doesn't matter how they do it. Somehow they know which blocks are free. So when your file gets larger, you can allocate more blocks, and they move from the free structure into your B-tree. And then if you make the file smaller or you delete a file, the blocks get recycled and they get moved back to that free space data structure, whatever it is. So why do we care about all this? Unfortunately, we're out of time in this video, so you're going to have to come back for our next video and find out why we care about all this information. Until then, thank you for listening.